Let knowledge flow like a river, without any hindrance. Don't make it like a stagnant pool. Hey everyone. I am PS Chatterjee with you, and I'm fired up to be back with your channel, Structural Design Only, a channel with different vision.
Power of Shapes, Part 4. Optimizing your design with Section Modulus. M by I equals to F by Y equals to E by R. This equation is fundamental to understanding how structures respond to loads. It's time to break it down. M by I equals to F by Y. We'll dive into the details of each component in the next slide. Don't miss out on this crucial knowledge. Hit that like button, share this video with your fellow engineers, and subscribe to our channel for more in-depth structural insights.
Title of this slide you are watching is, Understanding the Terms. Understanding the terms is essential for grasping the concept of section modulus. Let's start with bending stress, F, which is the stress experienced by a material when it bends. Bending moment is the force that causes this bending. Here we denoted bending moment as M. The moment of inertia, I, is a property of the cross-sectional shape that resists bending. And distance from the axis, Y, is the perpendicular distance of the extreme fiber from the axis, which is passing through the centroid of the cross-section. Title of this slide you are watching is, Assumptions for the equation. The equation M by I equals F by Y is a cornerstone in structural engineering. However, this equation is derived based on several key assumptions about the element and the loading conditions. Total 6 numbers of assumptions we have to consider here. In this slide we have 3 assumptions, and in the next slide we have 3 assumptions. Firstly, we assume small deflections, meaning the element bends only slightly under load. Secondly, plane sections perpendicular to the element's axis remain plane after bending. Third assumption, the element is subjected to pure bending without any additional forces. Now we are switching over to the next slide for next 3 assumptions. Title of this slide you are watching is, Understanding the Terms, second slide. Building on our assumptions, let's introduce some key concepts. Strain, represented by epsilon, is the deformation of the material under stress. It's calculated as the ratio of the distance from the neutral axis, Y, to the radius of curvature, R, of the bent beam. Next, we have stress, sigma, which is the internal resistance of the material to the applied force. It's determined using Hooke's law, where stress equals the modulus of elasticity, E, multiplied by strain. Finally, the bending moment, M, is resisted by the internal stress distribution within the beam. This resistance is quantified by the moment of inertia, I, a property of the cross-sectional area. Thus, bending moment equals stress multiplied by the moment of inertia. In our next slide we are going to establish the equation. Title of this slide you are watching is, Deriving the Equation. Now, let's see how the equation unfolds. We start by substituting the strain equation, epsilon equals to Y by R, into the stress equation to get sigma equals to E into Y by R. Next, we incorporate the bending moment equation, M equals to sigma into I. Substituting the value of sigma, we get m equals to E into Y into I, divided by R. Rearranging this equation, we find that m divided by I equals E by R into Y. Recognizing that E by R is a constant, we denote it as C. This simplifies the equation to m by I equals to C into Y. For convenience, we commonly treat this constant C as part of the stress term, leading to the familiar form, m by I equals F by Y. By rearranging this final equation, we arrive at the expression for bending stress, F, equals to m divided by the I by Y. Introducing the concept of section modulus, Z, as the inverse of Y multiplied by I, we can further simplify the equation to F equals m divided by Z. In our next slide, we will present a corrigendum regarding the moment of inertia calculations for triangles, trapezoids, and compound trapezoids, specifically about the ZZ axis. We will clarify some misconceptions and provide correct formulas for these geometric shapes.
Title of this slide you are watching, Corrigendum, regarding moment of inertia of a triangle about the ZZ axis. This is a correction to previous information provided by me, in my presentation, The Power of Shapes, Part 2. Now we are diving to the derivation of IGZZ, of a symmetrical triangle. Here you are watching image of a symmetrical triangle with base length b and height h. In our previous videos, we incorrectly stated that the moment of inertia of a triangular section about its centroidal axis is equal to the moment of inertia about an axis perpendicular to its plane. This is incorrect. Let's derive the correct formula for the moment of inertia of a triangle about its base, which we will consider as the ZZ axis. The moment of inertia of each half of the triangle about its base is given by I base equals to b into h cube by 12. For a symmetrical triangle, h equals to b by 2, by substituting this value. I base equals to h into b by 2 whole cube by 12 equals to h into b cubed by 96. The moment of inertia of the entire triangle about the ZZ axis, IGZZ, is twice the moment of inertia of one half. Therefore, finally we have IGZZ equals to 2 into h into b cubed by 96 equals to h into b cubed by 48. Title of the next slide is Corrigendum, moment of inertia of a trapezium about the ZZ axis.
Title of this slide you are watching, Corrigendum, regarding moment of inertia of a trapezium about the ZZ axis. This is a correction to previous information provided by me, in my presentation, The Power of Shapes, Part 3. Now we are diving to the derivation of IGZZ, of a symmetrical trapezium. Here you are watching image of a symmetrical trapezium with bottom base length A, top base length B and height h. In our previous videos, we incorrectly stated that the moment of inertia of a trapezium section about its centroidal axis is equal to the moment of inertia about an axis perpendicular to its plane. This is incorrect. This section is the combination of two right-angled triangle and a rectangle. Say base length of each triangle E and height h, and for rectangle base length h and depth b. Let's derive the correct formula for the moment of inertia of a trapezium about its ZZ axis passing through the center of gravity. The moment of inertia of each triangle about its base is given by I base equals to b into h cube by 12. Here b equals to h and h equals to e. By substituting this value, we have I base of each triangle equals to h into e cube by 12. By applying the theorem of parallel axis, we can say, the moment of inertia of the each triangle about a line PQ parallel to base, IGZZ1. This line is nothing but the ZZ axis of the symmetrical trapezium. Therefore IGZZ1 equals to I base plus area of the triangle into perpendicular distance between base of the triangle and ZZ axis equals to h into e cube by 12 plus half into e into h equals to h by 12 into e cube plus 6e. Say moment of inertia of the rectangle about PQ is IGZZ2. Therefore we can write IGZZ2 equals to 1/12 of h into b cube. Say moment of inertia of the whole trapezium about ZZ axis, IGZZ. IGZZ equals to 2 into IGZZ1 plus IGZZ2, therefore IGZZ equals to 1/12 of h into e cube plus 6e plus b cube. Now we know the length of the bottom base of the trapezium equals to a, and top base of the trapezium equals to b. Therefore we can say e equals to a minus b by 2. By substituting this value of e, finally we have IGZZ equals to 1/12 of h into a cube minus 3b into a square plus 9 a into b square minus 5 into b cube. Title of the next slide is Corrigendum, moment of inertia of a compound trapezium about the ZZ axis. Title of this slide you are watching, Corrigendum, moment of inertia of a compound trapezium about the ZZ axis. This is a correction to previous information provided by me, in my presentation, The Power of Shapes, Part 3. Now we are diving to the derivation of IGZZ, of a compound symmetrical trapezium. This trapezium has two parts. Top portion is a symmetrical trapezium and bottom portion is a rectangle. Here you are watching image of a symmetrical compound trapezium with bottom base length A, top base length B, height h, and width of the bottom rectangle is c. In our previous videos, we incorrectly stated that the moment of inertia of a compound trapezium section about its centroidal axis is equal to the moment of inertia about an axis perpendicular to its plane. This is incorrect. Let's derive the correct formula for the moment of inertia of a compound trapezium about its ZZ axis passing through the center of gravity. Say the moment of inertia of the symmetrical trapezium portion about ZZ axis passing through the CG is IGZZ1 and for rectangent is IGZZ2. We already know, IGZZ1 equals to 1/12 of h into a cube minus 3b into a square plus 9 a into b square minus 5 into b cube, and IGZZ2 equals to 1/12 of c into a cube. Say moment of inertia of a compound trapezium about the ZZ axis is IGZZ. Since the z-axis passing through the CG of both, therefore, IGZZ equals to IGZZ1 plus IGZZ2. Finally we have the moment of inertia of the compound trapezium, IGZZ equals to h by 48 into a cube minus 3b into a square plus 9a into b square minus 5 into b cube plus c into a cube by 12. Time to put these formulas into practice with an Excel spreadsheet.
Welcome back to our Excel spreadsheet for practical calculations regarding section modulus and bending stress. Let's explore this dashboard. At the top row of the dashboard, you can input the dimensions of the shape you're working with. Below this row, there's a cell, labeled as check. If the dimensions you input are inconsistent or irrelevant for the selected shape, an error message will appear with a double question mark, and the cell color will turn yellow. Our first example is a square section. Although both sides of a square are equal, we've input B as 5 meters and D as 4 meters to demonstrate the error checking feature. As expected, the system has flagged this inconsistency. Let's correct this by changing D to 5 meters. Now, there's no error message. Given moments mx of 50 kN and mz of 30 kN, the calculated moment of inertia of the section IGXX equals to IGZZ equals to 52.083 meter to the power 4. Distance of extreme point from x-axis, yx, and from z-axis, yz, equals to 2.5 meter. The calculated section moduli zx and zz are both 20.833, and the corresponding bending stresses fx and fz are 2.4 and 1.4 kilopascals respectively. Our second example is a rectangular section. Let's change the shape to a rectangle. For a rectangle, B and D must have different values. We'll change B from 5 meters to 4 meters, keeping the same moments as before. The calculated moment of inertia of the section IGXX equals to 26.667 and IGZZ equals to 41.667 meter to the power 4. Distance of extreme point from x-axis, yx equals to 2 meter. Distance of extreme point from z-axis, yz equals to 2.5 meter. The calculated section moduli now show zx equals to 13.333 and zz equals to 16.667 as, resulting in bending stresses Fx of 3.75 kilopascals and Fz of 1.8 kilopascals. Our third example is a triangular section. Now we are changing the shape by the help of drop-down menu from rectangle to triangle. A triangular section is defined by its base, b, and height, h. Say, b equals to 5 meter and h equals to 4 meter. Now we are changing the value of mx from 50 kN to 30 kN and keeping mz as 30 kN. The calculated moment of inertia of the section IGXX equals to 8.889 and IGZZ equals to 10.417 meter to the power 4. Distance of extreme point from x-axis, yx equals to 2.667 meter. Distance of extreme point from z-axis, yz equals to 2.5 meter. With this change, the calculated section moduli now show zx as 3.333 and zz as 4.167 and unit is meter cube, resulting in bending stresses Fx of 9 kilopascals and Fz of 7.2 kilopascals. Our fourth example is a circular section. Now we are changing the shape from triangular to circular. For a circular section, the diameter, d, is the primary dimension, say d equals to 5 meters and the values of mx 30 and mz equals to 30 kN. The calculated moment of inertia of the section IGXX equals to IGZZ equals to 30.68 meter to the power 4. Distance of extreme point from x-axis, yx equals to yz equals to 2.5 meter. The calculated section moduli now show zx equals to zz and values are 12.272 and unit is meter cube, resulting in bending stresses. Fx equals to Fz and values are 2.445 kilopascals. Our fifth example is a symmetrical trapezium section. Now we are changing the shape from circular to a symmetrical trapezium. For a trapezium section, we need the bottom base dimension, A, top base dimension, B, and height, H. These are the primary dimension. Say, A, equals to 5 meters, B, equals to 4 meter, H, equals to 2 meter and the values of mx 30 and mz equals to 30 kilonewton meter. The calculated moment of inertia of the section IGXX equals to 2.988 and IGZZ equals to 9.375 meter to the power 4. Distance of extreme point from x-axis, yx equals to 1.037 meter. Distance of extreme point from z-axis, yz equals to 2.5 meter. The calculated section moduli now show zx equals to 2.881 and zz equals to 3.75 meter cube, resulting in bending stresses. Fx equals to 10.413 and Fz equals to 8 kilopascals. Our sixth example is a symmetrical modified trapezium section. Now we are changing the shape from symmetrical trapezium to a symmetrical compound trapezium. We already know that this type of section are the combination of two sections. At the top we have a symmetrical trapezium and at the bottom we have a rectangle. For the trapezium section, we need the bottom base dimension, A, top base dimension, B, and height, H, and the dimensions of the rectangle are length, same as the bottom base length of the trapezium and depth of the rectangle, C. These are the primary dimension. Say, A, equals to 5 meters, B, equals to 4 meter, C, equals to 2 meter, H equals to 2.5 meter and the values of mx equals to 30 and mz equals to 30 kilonewton meter. The calculated moment of inertia of the section IGXX equals to 34.878 and IGZZ equals to 32.552 meter to the power 4. Distance of extreme point from x-axis, yx equals to 2.333 meter. Distance of extreme point from z-axis, yz equals to 2.5 meter. The calculated section moduli now show zx equals to 14.948 and zz equals to 13.021 meter cube, resulting in bending stresses. Fx equals to 2.007 and Fz equals to 2.304 kilopascals. We have explored section moduli and bending stresses for squares, rectangular, triangular, circular section and symmetrical trapezium and compound trapezium in Excel. You have it. We've successfully calculated section modulus using Excel. This powerful tool makes complex calculations a breeze, allowing you to optimize your designs efficiently. Remember, understanding section modulus is crucial for creating robust and cost-effective structures. Hit that like button if you found this helpful, share it with your fellow engineers, and subscribe for more in-depth structural engineering tutorials. Your support fuels our passion for creating valuable content. Thank you for watching.